Good morning to all of you. I would like first to thank the organizer to give me the opportunity to present this work and to give this talk. So today I will speak about the development and application of multiplex immunoassay as a diagnostic tools in ecotoxicology. The field is a little bit different that we see during this congress, but you will see we're still using XMAC technology. So the development of this assay is a part of a larger program which is named its Proteogram project. This project is in the field of ecotoxicology, because as you may know, hazard assessment of endocrine disruptor is a main concern today for public institutions as well as for all the population, and it is very important to know and to have tools to follow this pollution and the effect on the environment. With this aim, one of the team of the consortium are using a small gammarus, a small invertebrate, which is called Gammarus fossarum, which is known as a sentinel species to follow the pollution of aquatic media. Because this species is well known and well diffused and has a large space, is a trophic system, it is very sensitive to all pollution and can be used as a biosensor. In this aim, in this big project, even if this small invertebrate is well used, it is not the genomic data are not well known. So in this project, we try to identify specific protein of this invertebrate to propose endocrine descriptor biomarker that can be used for following pollution. And after that, we try to, when the biomarker were identified, to develop a multiplex assay to quantify this biomarker. As it is said by a lot of speakers, it is always necessary to have a fast and cost-effective technology to quantify biomarker. And in the field of ecotoxicology, generally, there is a lot of diverse methods, and direct method, but not multiplexed methods. That's why we were focusing on multiplex technology. You can use, of course, HPLC, MS technology to follow biomarker, but it's a little bit more difficult to transpose in all field. So the first steps was to identify the K protein in the Gammarus fossarum, and for that we use a quite recent approach, which is named the proteogenomic approach, to identify K protein in the organ reproductive function. This approach is a parallel combination of a deep RNA sequencing, where you try to identify protein encoding gene, and in parallel a large shotgun Tondes mass spectrometry analysis to see if the protein you identify are present through their proteolytic peptide. So with this approach and a lot of work, we could identify 1,873 protein in the male and female reproductive tissue, and 204 were present significant sexual dimorphism, which can be good for biomarkers, and especially for biomarker in endocrine with endocrine descriptor, which perturb mainly the reproductive system. So after that, we verify that these biomarkers are influenced by endocrine descriptor, and we choose 3 components which were representative of the modifications that can be induced when an invertebrate is exposed to endocrine disruptor. We follow during this exposition study 871 protein, among them the 224 protein identified with a strong sexual dimorphism. And we find that 70 proteins show significant variation through the exposure of the pollutant. Among them, 44 were common to the 3 pollutants, and 15 of the 44 was our protein that we identify with strong sexual dimorphism. So these ones could be used as a potential ED biomarker. Following that, we decided to select at the beginning to have a proof of concept of our approach to follow the protein by multiplex Luminex technology. We select 5 proteins. 2 are vitellogenin protein, which are precursor of protein egg folk, and 3 other are involved in either the reproduction, for this one which play an important role in calcium homeostasis for the sperm production, or in to control sexual development by sex splicing in the Gammarus. When at this stage we didn't want to develop antibodies against the protein, but against the peptide which are which represents the protein. So we selected several prototypic peptides for around 5 and 6 by protein, which were identified by HPLC-MS spectrometry. And we apply on this peptide several tests to select the best one for the immunization. We first checked that there was no, it was very specific of the species, no redundancy in the protein sequence database of the NCBI. We look with a software which was developed by one of our collaborators about parameter for immunogenicity, which means that the structure of the peptide, the position on is the protein, and is lipophilia or hydrophobicity. And we look also of potential site of N-glycosylation and O-glycosylation site, because we want to avoid this glycosylation in our selected peptide. With this project, we select one proteolytic peptide by protein, and we begin the immunization. As it was for this first step of proof of concept of our approach, before, as a Luminex assay, we decided to use competitive immunoassay. We didn't use to use a sandwich immunoassay because we didn't want to prepare pair antibodies, and so we decided to use a competitive immunoassay where the primary antibody will be detected by a secondary one biotinylated, and the reporter will be identified through the streptavidin ficoerythrin reporter. So the process will be the same for all of the presentation. At the first step, we mix the couplet bed with the primary antibody and the standard of the sample. After incubation, there is a wash step. Then we add the biotinylated secondary antibody. After incubation, a second wash procedure, and then addition of the streptavidin ficoerythrin conjugate before the last step and the read on the Luminex analyzer. We first decompose all these steps and not want to mix everything at the first stage to study all the parameters, and you will see that we made a lot of study about that. So first of all, there was the production of the antibody, then the optimization of the assay, and the validation procedure. As I said, we made the polyclonal antibodies, immunization on rabbits. We synthesized the 5 selected peptides. They were conjugated to BSA as an immune protein, carrier protein. We check every time the coupling range of the peptide on the BSA, and then for each peptide we immunize 2 rabbits over 3 months and 4 injections on French adjuvant. For each protein, we then have one peptide as used as a biomarker, and two sera for each one. As you can see, the peptide was the various length from 40 amino acid to 23 amino acid to 27 amino acid. Immunization proceeded well. There was no difficulty to have good or medium response. There were some EC50s up to 130,000 for the titers. And then we proceed to the development of the assay using directly the serum without purification for the assay. As I'm a chemist, I will show you a little bit of chemistry. So we decided to couple the peptide with a tile residue. So we introduce at the end terminus of our sequences a cysteine, and we prepare a malamide modified microsphere. It was, to note, it was our first time to use Luminex technology, so we discover everything, and we follow strictly the XMAX cookbook when we begin, which was a precious guide at the beginning. So when we couple the bead, an important thing that I would like to underline today is that it didn't mention, but we have to add a reducing agent to be sure that all the disulfide bond was break and the couple was efficiency. Before using systematically this reducing agent when doing the coupling, we were faced to not reproducible bead coupling. So we made the bead, and as everybody, we tested for the first time the coupling efficiency. We vary the amount of peptide per beads during the coupling phase, and we test rapidly the different dilution of serum and the different dilution of secondary antibody. To this stage, everything was okay. We had a nice fluorescence intensity without peptide, because as we work in competitive steps, the more we have fluorescence, the less there is some peptide. So, and we rapidly test some displacement assay to see if everything was working. The first assay were a little bit disappointed because we find an LLOQ of 50 nanogram per ml. We were used to develop a lot of ELISA in the lab, and generally speaking, the first assay was far more better. But anyway, what's surprising us is that even at our strong concentration, there was not a lot of, there still remain a high fluorescence intensity, and because the bead was not fluorescent at all when there is nothing coupled on it. So we try to increase the concentration of the peptide to displace completely the complex between the bead and the antibody. And even at the very strong concentration of the peptide, we have no displacement. So that was a little bit strange for us. The first study was done on peptide 5, and when we try another peptide to check, it was even far worse. We have nearly no low fluorescence intensity for the same coupling ratio and low displacement. So we suppose at this stage that there was an interaction between our antibody and the bead. And we check the carboxylated bead, the bead provided without modification. As expected, there was no interaction, and we have a max of fluorescence of 110. But when we incubate our malamide modified microsphere with our sera, we were faced with a strong fluorescence intensity in all the cases, and it varying depending the sera. That means that there was strong interaction between our malamide modified microsphere and the antibody. What we imagine that maybe the antibody proteins contain cysteine that can react to the bead and covalently couple the as it is used couple the antibody, and the reaction was not completely done. So what we did, we tried to block the limit microsphere with a thiol molecule to deactivate the myeloid function, and then we realized that all our interaction was far diminishing. So that means that we don't have any more coupling between our antibody and the microsphere. So we get back to the procedure of the coupling of the microsphere, and after coupling the peptide, we introduce a saturation step with beta-mercaptoethanol to be sure to block all the malate function that remain not functional by the peptide after the coupling. We use a strong concentration. We use various concentration. We find the optimal concentration, and as you can see on this slide, when we do this procedure, for the same coupling ratio between the bead, you have a strong displacement. Now you can nearly extend all the fluorescence signal. And what was more interesting and what was quite amazing at the first time, that for the other peptide, you have also an increase of the fluorescence intensity without when you don't add peptide. This effect was quite reproducible, and we can observe this effect with various peptides. We didn't really explain why, but maybe there is a position or the better dilution of the bead that can favorize the interaction between the bead and the peptide. Then we continue our assay development, and as it is a competitive assay, we say to improve the sensibility, we have to decrease the coupling ratio. However, when we decrease the coupling ratio, we were first with a diminution of the signal intensity, that is logical, but the impact on the sensitivity was not so good. So we could not really decrease a lot the coupling ratio between peptide and bides, because at one point we have no more signal and a not so good LLOQ. So what we do again, that we come back to optimization, and we try several chemical spacer to see if there was an effect or if we can improve that. And so we tested several chemical spacers that was available on the market. So it is recommended to use this one, the MPBH spacer, but you can find also this one with a longer arm and without this aromatic residue, or a smaller one. And this time, we find also that there was strong differences for a similar coupling ratio to the bead. If the bead were modified by KMH or EMCH, there was a strong fluorescence intensity a stronger intensity than with MPBH. However, at this stage, all LLOQ was similar. But starting with a stronger fluorescence intensity, that can allow you to decrease the ratio between the peptide and the bead, and that what we done for several peptides. So here I present you the tendency. It's not to see exactly what's happened, but if you see on this peptide, here there is a coupling ratio. And what you can see on this slide is that when you decrease the peptide ratio, you have a strong impact on the fluorescence intensity with the MPBH modified microsphere, here in blue and orange. However, with the KMUH coupled microsphere, you have not a so strong diminution of the signal. You get a diminution at white point, it's logical, but you have a stronger intensity. This can be observed with all our peptide and all our antibody. For this one, I won't show you everything, but I show you this one, for example. For this one, you can see MPBH coupling sphere with the two serum. The two sera, you have a decrease when you decrease the amount of coupling, but this decrease is less marked with the KMUH modified microsphere. So that means at this point that we realize that we have also to take care about the chemical spacer to improve and to optimize our assay. to make a long story short, at this point, we try a lot of combination with all our peptide and our sera to find the best chemical spacer for each peptide and for each combination of antibody. However, since the beginning, we have an aggregation problem with the bead. We didn't look a lot at that because we still can get signal and responses, but it was a little bit problematic. And we decided at this point to try to modify or to try to optimize and dip to the buffer to minimize the aggregation problem. As you can see, the apparatus report an average of 40% of aggregation, which is quite a lot and sometimes could block your analysis. It was different between the linker for the same coupling ratio, and it was different between the peptide. On the XMAT cooking book, the advised surfactant is a twin-20. It is used to avoid the aggregate. Among a lot of things, to avoid the aggregation of the beads. So we decided to test various concentrations of this surfactant as well as other surfactants. As you can observe, when you increase the concentration of the surfactant, of course, you can detect a diminution of the aggregation. It's not true for everyone. For example, with this chemical spacer, the aggregation remains strong. And for the 2-KMUH and MPMH, there is a diminution. There is also great differences between the surfactant. If we use another surfactant, we have less aggregation problem, and another one is also the same. As you see, the response is different between the arm and the peptide. However, we try also some combination to improve the aggregation problem. However, we found that the triton was a base compromise between all our peptide. I didn't show you all, and we decided for also not to use too much surfactant, to use 0.4% of triton for all our assay instead of twin-20 at 0.02%. Then we screen also secondary antibody and phycoerythrin conjugate from different providers. We would like to reduce our procedure, and as we use biotin, secondary biotin-related antibody, we try also antibody which was directly labeled with phycoerythrin. And at the initial stage, we use an entire immunoglobulin which detects the whole rabbit molecule. We try to find other immunoglobulin which will detect only H and L chain or only FC fragment specific. We try also smaller and part of the antibody to try to improve the number of secondary antibody on the bead. But the first we used was the best. There was no significant difference between all the secondary antibody, and even the antibody which were directly marked with the phycoerythrin was not so efficient for the same concentration. We use all this, of course, at the same concentration during the incubation step. As you can see, for the R-phycoerythrin conjugate, there is not also a lot of difference. The main difference is between the two sources of SAP conjugate provided by Thermo Fisher. There is one, which is more expensive, of course, which is said premium grade because it's best purified and they remain unlabeled molecule. And there is a strong difference between these two. If you have to use one, prefer the premium grade because it gives you the result. The fluorescence are higher and also the reproducibility is better. Then we finalize all our conditions, and we begin to validate all our simplex assay. As you can see, so we follow the procedure of the XMAX cooking book and all the normal procedure of validation of an assay. I will report you only some detail. When we try to do our calibration curve during 3 days, as you can see, there is a good reproducibility in the LOQ without a CV which is perfectly acceptable. It was interesting to see that even if you change the lot of preparation bead, you don't have any variation. So that means that we are able to control the coupling procedure and be reproducible. We try to do also the recovery assay, and in all the cases you can observe a good recovery from 80 to 115 with an average of 100, which was we expected. So at this point, after the validation of all simplex assay, we decided to, of course, multiplex the assay. So before doing that, we want to be sure, even if the peptide was very different and was selected to be very different, that the antibody do not cross-react with the bead. So we test for each bead coupled with one peptide all our sera to see if there was a recognition of the other sera to the bead. Fortunately, there was only one, and we don't know why, but it's like that when you produce antibody. There was one we can cross-react with another peptide. All our antibody was specific for their own peptide. As you can see, there is in each series there is only one which recognizes the bead. You can also still observe some differences between the MPBH modified microsphere and the Gammarus microsphere, where you have a stronger signal, whereas the coupling ratio is the same, which we check also with the pool to see if there is some effect or some different effect on the signal, but not. So at this stage, the first steps was okay. We test also to see if our peptide could displace preform bead, peptide couplet bead and antibodies. Unfortunately, in this case also, only the peptide, which was the corresponding peptide of the bead, could displace the antibody peptide couplet beads. Here we focus on only the ratio of we normalize with the ratio of the signal, the fluorescence signal between the bead and the sera without peptide, and we use a stronger concentration of the peptide to displace, to try to displace. We try also to do it with the pool of peptide, which each one with 500 nanogram microliters, and as you see, even when there was all the peptide, there is no displacement. So it was okay. It was okay for all the sera and quite reproducible. We study the kinetic of the reaction because we would like to do the shorter time of incubation. We try to see the evolution of the signal without peptide and the variation of the LLOQ and the ULOQ. It appears that 4 hour time, the time we selected at the beginning, was the best, and because you see that there is the kinetic of the reaction is a little bit different between the antibody, but you have nearly a stabilization around 4 hours, and then it's at this point that you can observe the best ratio between the LLOQ and the fluorescence intensity. So we validate our assay in quadruplex assay. That means that we check all the LLOQ. And as you can see, the LLOQ, we begin with LLOQ with 49 nanogram per ml, and we finish with an LLOQ with 100 picogram per ml, with the same antibody, only optimizing the condition. All assay was validated, so we tested now on our Gammarus fossarum. So the step is you extract the protein for the gamma, you do a trypsin digestion to liberate the peptide. You do then either a simple purification on SPE or a more, precise purification on gel. And then you do the analysis. We first do a standard addition method to see if there is no matrix effect. Everything was okay. There was no matrix effect. There was a good recovery for all the peptides. So it was nice for the assay. That means that we can use the assay in a complex mixture of a lot of peptides and non-digested protein. And here I present you the primary result of our quantification. There was a lot of optimization to do to have this result, but I won't detail then. And then we have for some of them a good correlation between the concentration that we can quantify in the gamma and the number of quantic peptides that are detected in the peptide, in the same sample, which is a good indication, but not completely proof, but it's interesting. It is not the case at this stage for all the peptide. We test the concentration of the peptide for our biomarker comparing the female and the male gammarid. There is only a small number of results, so the analysis is not very significant, but at this stage we can see a significant difference between the male and female for one vitellogenin biomarker, which is interesting because vitellogenin is more a marker of female. And that will be all for today, because now we are continuing our assay to a larger number of gammarid, and we are trying to follow our biomarker through the cell cycle of the gammarid, because we know that there are some variation, especially in vitellogenin and other. We are trying to expand the number of biomarkers. Now we pass on phage display technology to produce our antibody. We stop immunization on rabbit. And what I will say that to conclude is that if you want to develop a Luminex assay, you have to pay attention very carefully to all of the parameters. It was the first time that we did this, that we use this technology. Now I can say that in 3 weeks I will be able to do a good assay, but it takes more than 1.5 years to do everything. So there is a lot of parameters, a lot of tips to take into account to develop this assay. Competitive multiplex assay at the end is a good format to quantify in complex mixture. You don't need to have pair antibodies. And I won't go back to ELISA now. And we are trying to expand this technology to other applications, but not in the pharmaceutical field, in other fields, because we want to develop this application in non-use field at least. So I would like to thank you. Thanks again to Luminex for inviting me. I would like to thank especially Cécile, which our engineer will do all the work, as we are now very confident with the Luminex technology and our financial support. Thank you very much.